Okay, so we've been talking about measuring angles and dealing with angles in this form. 18 degrees, 43 minutes, 29 seconds. And we know that's just a different way of expressing an angle that's between 18 and 19 degrees. We refer to this as DMS notation, or degrees, minutes, seconds. We can convert it to DD, or decimal degree notation. And let's go ahead and do that. So we're going to take that 18 degrees, 43 minutes, 29 seconds. And I'm going to do it in my calculator. So I'm going to slide my calculator over here so I can see the problem. So when I'm going from degrees, minutes, seconds to decimal degrees, I start at the end of the number and work backwards. So I have the 29 seconds. I take the 29. I'm going to divide by 60 to make it minutes. So I have turned the 29 seconds into 0.8333333 minutes. Well, I had 43 minutes there before, so we're going to add those 43 minutes to that decimal. So technically what this is right now is this is 18 degrees, 43.48333333 minutes. That's what that calculator is showing. So now I've got to turn that 43.483333 minutes into degrees. I do that by dividing by 60 again. It's 0.7247 degrees. So I'm going to add the 18 degrees I already had. Of 18.4247 degrees. Remember, when we're doing decimal degrees, 4 decimal places is what we desire. I want to go the other direction. I have something like 29.3971 degrees as decimal degrees. And I want to go to DMS, degrees, minutes, seconds. Well, we'll keep my calculator over here. We're going to reverse the process. We're going to go exactly the opposite direction. The last thing we did here was to add the degrees on. First thing we're going to do, going the other direction, is we're going to subtract those degrees off. In other words, we're taking the 29 degrees, and we're just keeping it. So I subtract off the 29 degrees. I'm left with just the decimal portion of the degrees. Now I'm going to turn that decimal portion back down into minutes. So I'm going to multiply by 60. I have 23.28 again. I'm just going to keep the 23 off of that. I'm going to subtract off the 23. Take that out. I have 0.826 minutes. I'm going to turn that into seconds by multiplying by 60. 49.56 will round up to 50 seconds. That's 29 degrees, 23 minutes, 50 seconds. We did some operations with these. I'm going to skip some of the simple stuff and go to some of the more complex things. One relationship we had would be between these two marked angles here. Those two angles combine to make a line, which means they have to add up to 180 degrees. The technical term is they are supplementary. So if I tell you that this angle over here is, what do I want to call that? We'll go 42 degrees, 19 minutes, 38 seconds. I can find this angle here because it's going to be 180 degrees, but I have to write it as 180 degrees, 0 minutes, 0 seconds, minus the 42 degrees, 19 minutes, 38 seconds. And now as I subtract, 0 minus 38, of course, can't be done, so I have to borrow. Nothing here to borrow from, so I go all the way to the 180. That'll become 179. That would make this 60 minutes here, but I need to borrow from that, so that's going to become 59 minutes, and this will be 60 seconds. Now we can subtract. 60 minus 38 is 22 seconds. 59 minus 19 is 40 minutes, and 179 minus 42 is 137 degrees. So that was the supplement of that angle. We know supplement because they add up to 180 degrees or a straight line. Well, next, we have this angle over here. Looking at that angle, we don't have any calculation that we have to do here because it's what's referred to as vertical angles. Those two angles there are on opposite sides of intersecting lines. Vertical angles are equal. So this angle here just has to be 42 degrees, 19 minutes, and 38 seconds. For a similar reason, this angle and this one down here have to be the same. They're vertical angles. So this angle down here is 137 degrees, 40 minutes, and 22 seconds. Addition and subtraction with those angles was one thing. Multiplication and division is a little bit different. Let's say I have 21 degrees, 39 minutes, 52 seconds. I'm going to multiply that by 4. We did 4 times 52 is 208, which is bigger than a minute. It's 60 seconds in a minute. Well, it's bigger than 2 minutes. 2 times 60 would be 120. 3 times 60 would be 180, so it's actually bigger than 3 minutes. That's 3 minutes. We're going to subtract the 180 seconds that used up, leaving us with 28 seconds. And we carry the 3 minutes. Now we have 4 times 139, which is 156, plus the 3 that we carried is 159 minutes. Well, 120 would be 2 degrees. So we've got 2 degrees that we can take out of there. We'll subtract out the 120. 159 minus 120 is 39 minutes. And we'll carry the 2 degrees that we had pulled out of there. Finally, we do 4 times 21, which is 84, plus the 2 that we carried is 86 degrees. That is not a short process, not a simple process by any means, but it's the same as our processes with other measurements, just a little bit larger numbers is all. So division is the one where we go the other direction. Let's say we have 71 degrees, 53 minutes, and 42 seconds. I'm going to divide that into 6 equal pieces. Well, 6 into 71 goes 11 times. 11 degrees times 6 is 66 degrees. We subtract 71 minus 66, there's 5 degrees left over. Before I can bring down my 53 minutes, I have to turn that leftover 5 degrees into minutes. 5 times 60 makes that 300 minutes. Now I can bring down the 53 degrees. 53 plus 300 is 353 minutes. Or sorry, bring down the 53 minutes, I should say. 53 plus 300 is 353 minutes. Now we got 353 divided by 6. 58 minutes. 6 times 58 is 348 minutes. We subtract there is, once again, 5 minutes left over. We turn that into seconds. 5 times 60 would be 300 seconds. I bring down the 42. That's 342 seconds. Six goes into 342. Exactly 57 times. That's 11 degrees, 58 minutes, 57 seconds. Well, today we want to continue working with our angles. First thing I want to look at is naming angles. We've done this a little bit, but I want to make it formal. There are three main ways to name an angle. So if I have this angle here, and I'll label points on the sides and the vertex. I could just call this angle B, because B is the vertex of that angle, and it's really the only angle on there with a vertex of B. However, if I added another line like this, now just saying angle B is a little ambiguous. There's multiple different angles that could be referring to. So a more specific way of referring to this angle over here is I could call it angle ABC or angle CBA. Notice in either case, the middle letter is again the vertex of the angle, the B. So I name a point on one side, does not matter which side, but I name a point on one side, then I name the vertex, and then I name a point on the other side. Now, if we have to name a lot of angles, that gets to be pretty clumsy to have to say angle ABC, angle ABD, angle DBC. A lot of angles to talk about. So we can shorten our notation a little bit and just put a mark in here like this. I put the number 1 in there. That would just indicate that is angle 1. Put the number 2 in here. That would indicate that is angle number 2. Again, if there's multiple angles, if I wanted to indicate this angle, that's a little more difficult to label now. I can put a 3 there, but it's not necessarily clear that that 3 refers to the whole big angle. So it is sometimes necessary to mix our notations. We've talked some about our relationships between lines. So that would be line AB, and our notation would look something like this. The arrowheads are indicating that it's a line. If it was no arrowheads, it would be a line segment, or one arrowhead, like up here. That one arrowhead would have been ray BC, which would have been this right here. I'm going to draw a second line here. Call it line CD. Oops. And I'm going to put it over here, line CD, because I'm going to explain the relationship between them. I got them a little crooked here, but the intention was for them to be parallel. That symbol is line AB is parallel to line CD. We've mentioned the term transversal. Sometimes a line is just labeled with a letter, by the way. We might call that line M. So in this case, notice that's a small letter where all of our points are labeled with capital letters. In this case, line M is a transversal. Now I am going to put points in here. Just so I can refer to some things. If I give you that this angle here is 71 degrees, find, now I'm going to introduce a little new notation here. Calling that line M might have been a little floppy here, but M with that angle symbol, if I ask you to find angle EFB, that is just talking about the angle EFB. Here's E, F, and B. That's just saying this angle. It's not asking you to do anything with it. It's just find it. Well, there it is. But if I say find M angle EFB, that M is standing for measure. In other words, find the measure or the measurement of angle EFB. It's asking you to find its size. Well, I know the size can be found because AB is a line, and those two angles, AFE and EFB, add up to that line, so they have to be supplements. 180 minus 71 is 109 degrees. Now that I have that, all the other angles here are going to be one of those two angles, either 71 or 109 degrees. So let's look at angle BFG. Which one is that one, 71 or 109? Yes, that's a 71. Angle AFG. Yep, that one is definitely a 109. Angle FGD. Oh, that one's also definitely 109. Angle FGC. FGC is that angle there. That's definitely a 71 degree. So you can see in a complicated figure like this, being able to name those angles makes it a little bit easier to locate them. Okay, so then let's talk about actually measuring an angle. All the angles we've looked at so far, I've given you the measurement of. What if I didn't give you the measurement? What if I gave you an angle? Said, how big is it? Well, there's a piece of equipment, measuring device, called a protractor. And I'm guessing all of you have seen them before. Maybe many of you probably used them before. A protractor is basically a half circle. And on the bottom of that half circle, there's a 0 point. Sometimes it's up a little ways from the bottom. Sometimes it's right on the bottom edge. And that is the location where we were supposed to put the vertex of our angle. So the vertex of this angle right there would go on that spot. So whichever one it is we're using. Let's say we're going to use the bottom one because 0 is right on the edge here. So you put that vertex right on that spot, and then one side of the angle has to go through one of the 0 points. So let me draw in the protractor on this here. A little bit better than that. There's the protractor. This is the 0 degrees, and this is my starting point marked. This will be the 0 point over on the other side. Of course, this is going to be 90 degrees. This is going to be marked 0 and 180. And we'll talk about the difference there in just a second. So this mark here would be marked 30 and 150. This would be marked 20 and 160. The reason is, depending on which side we are using as our 0 point, here we've put this side of the angle on the 0 on the left side here. Depending on which side, we would use one set or the other. If I had the 0 side over here, I would use the different set of numbers. The easiest way to remember which set of numbers to use is to look at the angle. Is this angle acute or obtuse? Well, it is an acute angle, which means it's less than 90 degrees. So it cannot be the 150 or the 160. So this is between 20 and 30. That would be 25, so it's looking like about 27 degrees is the measurement of that angle. Now your protractor will have markings in between, make it a lot easier. It's just hard to draw it out that way when I'm doing it on the board here. I'm going to assume you all have had experience working with a protractor. There will be some problems where you're asked to measure angles, so hopefully you have one. If you don't, I have one in the classroom, and on Monday, if we have a little work time, you can borrow it if you need to. The other thing we need to be able to do is we need to be able to use the protractor to draw an angle. Do that, we start out by drawing the first side of the angle and designating which end of that is going to be our vertex. Let's say the vertex is going to be at that red dot. So now I'm going to take my protractor and set it on that line. So that vertex is again at that center point, and the side that I drew, the rest of that side goes through one of those zero edges. And let's say I want a 60-degree angle. 60-degree angles are actually pretty common in construction. So I would go up here and I would find the spot labeled 60 degrees. And on the edge of my protractor, I'd put a dot there. Once I put the dot there, I'm going to take my protractor out. Don't need it in there anymore. I might use the bottom edge of my protractor as a straight edge or a ruler. I'm going to draw a line from my vertex through that point. That makes this a 60-degree angle. Again, I'm going to assume you guys have used a protractor and know how to use them so that we don't have to get into too much detail with this. We have discussed parallel lines. Parallel lines,
We got those in our draft.
Do you have the protractor in your packet?
We got them in our drafting kits.
Perfect. Parallel lines in 2 dimensions are often defined as lines that do not intersect. But as we've mentioned, in 3 dimensions, that's not adequate. If this is a line here and this is another line, they don't intersect, but they are not anywhere near parallel. So in 3 dimensions, just saying that they don't intersect is not adequate. In 3 dimensions, we have to say that they're always the same distance apart. Now, to measure the distance between lines, what we do is we pick a point on one of the lines. Let's pick that point on that first line. And we measure the distance to the other line. And that distance from a point to a line is measured at what we call a perpendicular. Remember, perpendicular is the right angle. So this little right angle down here indicates that that's perpendicular. So any point I pick on that line will be the same distance from the other line. Now, because these lines are parallel, if I switch things up, let's say I took this point on this line where that perpendicular intersected, the measurement to the other line is going to be the same distance. So it doesn't matter which direction you go or which line you pick a point on, the distance will always be the same to the other line. We talked about that transversal that cut across. If I give you this angle here as being 72 degrees, 18 minutes, 21 seconds. What's angle 2 have to be? Actually, let's skip angle 2. Let's go down here. Let's call this angle 5. What's angle 5 have to be? Well, remember, we discussed this when we have parallel lines that are crossed by a transversal. If we know one of the angles, which is what we have right here, if we know that angle, all the other angles are either equal to it or supplementary. Well, angle 5 is definitely not equal to it, so it has to be supplementary. So we do that calculation to subtract. So 180 minus 78 degrees, 18 minutes, 21 seconds. 101 degrees, 41 minutes, and 39 seconds. That angle. If I asked you for angle 7 down here, that one, of course, has to be equal. So that's going to be just 72 degrees, 18 minutes, and 21 seconds. I feel like I've been flying through material today, but we are almost done. The last thing I want to show you today is relationships between angles and sides that are parallel to the sides of those angles or perpendicular to the sides of those angles. It happens quite a bit in construction where we'll have a known angle. This might be a street corner or corner of a lot, corner of a building, intersection of walls, whatever. And let's say that I tell you that that is 74 degrees. Well, because of the layout of many construction sites, there's a lot of things that are parallel. So let's say that I have this line over here that is parallel with this line. I'm going to draw a line parallel to the other side of this angle. What are the possible angles that could be formed? Well, I could draw it parallel right here. That's going to be parallel to it. What's this angle going to be? Well, it has to be the 74 degrees. But you'll notice the way I drew that, there's a second angle that could have possibly been formed. This one over here would be the supplement of 74. 180 minus 74 would be 106 degrees. Drawing sides parallel to the sides of an existing angle gives me either an angle that's equal to it or supplementary to it. This here side, this line is parallel to the one highlighted in yellow. This is parallel to the red side. Forming an angle there, that one has to be the 106 degrees. Or I can have a side here parallel to the one highlighted in yellow. This one's parallel to the red side. That has to be 74 degrees. No matter what, any lines that are parallel to the sides of those existing angles have to intersect either in the same angle or the supplement. Another common theme in construction is perpendicular lines. Let's say I have an angle here that we're going to call it 128 degrees. I'm going to draw lines that are perpendicular. I'm going to make this side red, this side blue, so that I can refer to them. So this is perpendicular to the red line. If I extended it, it would hit at a right angle. This is perpendicular to the blue line. I'll just run it through so it goes through. Now we'll notice up here, this angle here is not 128 degrees. 128 is an obtuse angle. This is acute. But there is a relationship between them. This forms a four-sided figure there. Any four-sided figures have an angle sum. Now, we've talked about triangles have an angle sum. Their angles have to add up to 180 degrees. A four-sided figure has to have sides that add up to 360 degrees. So I have 90 and 90 there. Leaves me with 180 degrees. So from that, the only thing I'd have to do to find this other angle is I'd have to subtract that remaining 128 degrees, giving me 52 degrees. Well, once again, you see what it came down to was taking this angle and subtracting it from 180 degrees. This angle here is the supplement. Well, you might wonder, well, is that the only angle we can get? Well, no, we can get other angles. Let's extend this red side down here. And we'll go perpendicular here. And see it intersects that brown line there. This angle formed. If I look at this four-sided figure down here, this has to be 52 degrees because it's supplementary to the 128, because that is a line across here. Well, now for the same reasoning, I have 90 degrees here and here. I would take my 360 degrees for my four-sided figure. I'd subtract the two 90-degree angles. I'm left with 180 degrees. This has to be supplementary to the 52. In other words, 128 degrees. Notice that is the same angle as our original angle. So once again, if we have a known angle and we have lines that are perpendicular to the sides of that known angle, the angles that are formed will either be equal to the original angle or supplements to that original angle. I know at this point it's hard to see where that would be terribly useful, because in most cases the angles will be called out, but there are times where you need to slide things over or you want to change the orientation of something. This makes it a lot easier to do that. Okay, I feel like I've been talking fast and crammed a lot of information into 35 minutes here. Let's give you some homework. So this is all out of the big book. Page 542 through 544. Exercise 20-3. 7 through 15, the odds. Page 545 through, just page 545, I guess. Exercise 20-4. 1 through 23, the odds. Page 550 through 551. Exercise 21-3, I should say. 1 through 27, the odds. And finally, this is the last one, I promise. Page 555 through 557. Exercise 21-4, 1 through 13, the odds. These should go pretty quick. They are just finding missing angles. It's a matter, in most cases, of figuring out whether they're equal or supplementary. A little bit of angle operations, but not too bad. So with that, I will give you our last 30 minutes here or so to get started on that homework. I'll be on the network here to answer any questions if you want.